We've made it to the end of chemistry. We're in our final unit, all about nuclear chemistry. It sounds probably pretty scary and intimidating, but it typically is a unit that students find a lot less strenuous, especially up until what we've been doing for until now. So it kind of is a great way to end the semester with something a little bit more chill and actually, pretty kind of exciting when we're talking about, radioactivity and stuff like that. It will be a lot of throwing back to when we learned about atomic structure, because we're going to be focusing on some of the subatomic particles within the atom. Okay, so with that being said, let's maybe do a review here. What subatomic particles are located in the nucleus? It's been a hot minute, so let's look at atom here, you guys. In the nucleus, I have two things. I have a red thing with a positive charge, that is called a proton, and I have a blue-looking thing with no charge at all. That is called a neutron. Okay, spiraling around outside of this nucleus is going to be my electrons. So the subatomic particles that are located in the nucleus are my protons and my neutrons. Okay. What are isotopes? You were like, oh, no, here we go again. Well, here, let's just look at this picture. These are 3 isotopes of carbon. Carbon is all carbon, okay? But it can come in different flavors or forms, particularly isotopes, okay? So this is the isotope carbon-12, this is the isotope carbon-13, and this is isotope carbon-14, okay? They are all carbon, which means on the periodic table, you will see a big old 6 next to the symbol of carbon, and that just means that there are 6 protons. That atomic number represents the number of protons within an atom. Okay, now where they're different is I have it mapped out down here. The number of neutrons are different. Okay, so isotopes are atoms of the same element. These are all carbon that have a different number of neutrons. Okay, and as a result, I know that that number that I'm writing here is a mass number is the sum of the protons and neutrons put together. So that number after the dash represents the mass number. Okay, so as a review, our subatomic particles are my proton, my neutron, and my electron. They also have maybe a charge, okay? Protons have a positive charge, which is why you'll often see a little P with a little plus sign up there, okay? Neutrons have a neutral charge, not positive or negative, they are neutral. And then electrons do have a negative charge, which to the symbol E, you will have a little minus sign, okay? So that means that these are the charges I'm looking at coming in with the atom. Okay, now the one thing I do want to mention before we move on is when it comes to the subatomic particles in the nucleus, the protons and the neutrons, they are the only ones that have comparable mass or significant mass for us to study, okay? So if I were to go back to this last slide and focus on, well, why do we call that mass number? Well, the mass number is the sum of all of the subatomic particles that do have mass. So noticing that does not include the electrons. Anyway, okay, so now focusing back on the nucleus here. The nucleus is made up of nucleons. So we can put protons and neutrons into a category and just say, y'all are nucleons, okay? And so when we study nuclear chemistry, we're studying this part of the atom, those nucleons, and we tend to refer to the atom as a nuclide. Lots of terminology here. Don't get too twisted up about that, okay, you guys? But a nuclide is a way or a specific type of item defined by only what's in the nucleus, meaning the number of protons and neutrons, okay? So if I were to look at this carbon atom that I had here, I'm looking at those electrons. That is all great and fun, but in nuclear chemistry, we don't care about the electrons. We only care about what is going on in the nucleus. So we care about the nuclide, okay? I can represent what's going on in a nucleus with 2 ways. This is nothing new, but it has been a while, so we're going to review it, okay? This is how I can represent the subatomic particles, meaning the protons and the neutrons specifically within an atom, okay? Here I have radium, hopefully that's the name of the element, and then after the dash, I have a number. This number is the mass number, okay? Mass number is the number of things that have mass, meaning your protons and your neutrons, which are the nucleons, the stuff that's in the nucleus. That is important, hopefully, for nuclear chemistry. Or I could take this exact same information and represent it here as nuclide notation, okay? Where here is the atomic symbol for radium. Up here is my mass number, meaning the sum of my protons and my neutrons. And then down here is my atomic number, and that will be that big number that you see on the periodic table matching with that elemental symbol. But atomic number does mean the number of protons. Okay, so it has been a minute, so let's practice. I'm actually going to pull out my periodic table so you guys can track along with me, because some of this may involve us like finding things. So here I'm giving a nuclide symbol here of carbon and then 14 and then there is 6. You're like, what has even happening here? Well, I even, spoiler alert, gave it away. What element is this, you guys? I think we can find the C on the periodic table and see that that is in fact carbon. Okay, so I get that information from the letter, right? What's the mass number? The mass number you're not getting from the periodic table. You're getting from something in the symbol notation, okay? And that symbol notation number that we are looking at is 14. That's the number of protons and neutrons in this specific nuclide. What is the atomic number? You guys, atomic number is that bottom number in the nuclide notation. It is also your atomic number on your periodic table, okay? Speaking of that atomic number, I can now maybe figure out how many protons and how many neutrons does this nuclide have. Well, how am I supposed to ever do that? That atomic number means something. It tells me how many protons I have. I have 6 protons. Well, how am I going to figure out the neutrons? You guys, that's where the mass number comes into play. The mass number, that 14, is the number of protons and neutrons together. And then from that, I can subtract the number of protons to get the number of neutrons, which is 8 in this case. Amazing. Okay, let's see. Let's do one more. No, maybe 2 more. We'll see. It's going to go a little bit faster now that we are realizing that we remember some things maybe from last semester. Okay, so here we go. It says 209 PO. You're like, oh my gosh, what is happening here? Well, what element is this? If we look, and it may be a little bit more challenging because this element is not very common. I almost said it. Okay, I see it right here on the periodic table, and notice that this is the element polonium. All right, what is the mass number? The mass number is that tippity top number up here. It is 209. There are that many things that in the nucleus. What is the atomic number? You were searching for it right here. You were like, oh, no one can know. She did not give me that number. It is a 0. No, it is not a 0. If that space is left blank, you do have the ability to figure out and fill in that space. It is the atomic number that you will always see that defines the element on your periodic table. So that means it is atomic number 84. Yes? Okay. Then I can use this information, just like we did last time, to figure out how many protons and how many neutrons does this nuclide have. He's got 84 protons. That's the atomic number. Yep. And to figure out the neutrons, I subtract the mass number minus the number of protons, and then I get the number of neutrons. And I really like how in the nuclide notation they are stacked right on top of each other. It's kind of set up perfectly for a little subtraction step to help you remember how to solve for your neutrons. All right, last little practice before we move on. I can give it to you in this form, okay? This says cobalt 60. The first question is going to be really easy to answer. What element is this? Is cobalt, you guys. Great, we can read. What's the mass number? The mass number is the number after the dash in this notation, okay? What is the atomic number? I do not see any other numbers in this notation besides the 60, but you can always find the atomic number on your periodic table. He is right there, so he is atomic number 27, right? Okay, how many protons and how many neutrons does this guy have? He's got 27 protons. That's what the atomic number tells me. And to find the neutrons, I subtract the mass number minus the number of protons to get the number of neutrons as 33. Amazing review. Okay, but do not trust atoms because they make up everything. Okay, so with my subatomic particles, we know we maybe potentially have some charges here. We know that opposite charges attract and like charges repel. So what that means, if I have a positive thing and a negative thing, they're going to attract each other. Or if I have 2 positive things or 2 negative things, they're going to repel each other. So looking at the nucleus, I know a nucleus is made up of positive protons and neutrons that don't have any charge at all. So why is this nucleus able to stick together? In other words, why doesn't the nucleus fall apart if all of the positive protons are going to repel each other, right? Well, this brings me to the nuclear force. So neutrons, yes, they insulate these positive repulsions between protons. They're like, buffer it a little bit, but they also help create this short range, really strong binding energy called a nuclear force. That nuclear force pulls everybody in super tight. That force is extremely strong and is going to make that nucleus stable. So looking at my cute little cartoon, I have my proton and my neutron, and they're held in with that strong nuclear force. And my little electron, he's just out here chilling in the electron cloud. So that's what makes a nucleus stable. But what's cool is that what happens when the nucleus is unstable and what conditions lead to that.
How do you know if an atom is stable? In this video, we're going to learn about radioactive decay. An atom is composed of subatomic particles called protons, neutrons, and electrons. Positively charged protons and neutrons with no charge from the central nucleus. Negatively charged electrons orbit the nucleus. A strong nuclear force holds the positive protons and neutral neutrons together in the nucleus and is what determines if a nucleus is stable. In stable nuclei, the force is strong enough and brings sufficient energy to hold the nucleus together permanently. Unstable nuclei either have too many protons or too many neutrons, upsetting the strong nuclear forces. Unstable nuclei try to balance themselves by giving off the excess proton or neutron. This is radioactive decay. Unstable nuclei are radioactive and emit radiation. So how do we know if an atom is stable or unstable? We can determine whether a radioisotope is likely to decay and what type of decay is likely to occur by looking at its position on a proton-neutron NZ graph. This graph shows the number of protons on the x-axis and the number of neutrons on the y-axis. This is the stability line. If a radioisotope lies left or right of this line, it is unstable and likely to decay to become stable. A radioisotope that lies to the left of the stability line has too many neutrons and is likely to undergo beta- decay, so give off electrons. A radioisotope that lies to the right of the stability line has too many protons and is likely to undergo beta+ decay, so give off positrons. If particles have a high number of protons, usually more than 82, they are likely to undergo alpha decay.
Okay, so what this means is that for each atom on the periodic table, there is kind of like an optimal range of the ratio of protons to neutrons. Now, if this nucleon ratio does not fall within what is called a band of stability, then the nuclear force between those protons and those neutrons weakens, and that nucleus is actually unstable. So if I look at this here, that little blue line represents the number of protons to neutrons that I need to make a nucleus stable. Keeping in mind the number of protons defines what element you are, so each element has a optimal range of protons to neutrons, okay? So if you lie relatively within this stability band, you are closer to being stable and that nucleus will not fall apart, okay? If you notice here, this black line right here would represent what a 1-to-1 proton-neutron ratio would be. So as we have lighter elements, right, that 1-to-1 ratio is preferred for the most part. But as we get bigger and fatter and heavier, it looks like we need more neutrons than protons to be within that optimal range, okay? So zoning in a little bit more on this one little indicated section here in red, I can look a little bit more closer at that blue line, and we would call that stable nuclei non-radioactive, okay? In the video, they talked about the different kinds of radioactive decay, and that's what this chart is here showing: the beta emission, positron emission, alpha emission. We're going to get in there here in a little bit, but this is just showing that the radioactive decay occurs as a result of the atom being unstable and not being perfectly within that line of stability. Okay, so the nucleus responds to its instability by undergoing a process called radioactive decay. And this is the spontaneous decomposition or transformation of an unstable nucleus into a more stable form through the release of a subatomic particle and or just energy in the form of electromagnetic radiation. Now, when I mean particle, I mean either like an electron or a proton or a neutron or something like that shooting off of the nucleus, a subatomic particle. Energy is just electromagnetic radiation, okay? So this is kind of the summary of where we're going with this. These are the main 5 types of radioactive decay. We have alpha decay, beta decay, gamma decay, positron emission, and then electron capture, okay? We're going to unpack this here in a second, but I want us to focus on this business right here. Y'all are like, what? A nuclear equation? What does all of this mean? Well, do you mean we have to write and balance equations for nuclear reactions now too? Yes. But y'all, don't worry, it will actually be fine, I promise, okay? It's actually a lot simpler than chemical reactions. But let's kind of now remind ourselves what a chemical reaction is and how that might be different than a nuclear reaction. So a chemical reaction involves the breaking and forming of bonds between different atoms. Now, keep in mind, bonds involve the electrons, okay? Nuclear reactions involve changes within the number of subatomic particles within a single atom, specifically the nucleus, okay? So chemical reactions, we all about electrons in forming and breaking bonds, okay? If you'll notice, I'm looking at in this chemical reaction between methane and oxygen to produce carbon dioxide and water, I've got different elements making bonds and breaking bonds. But down here, and I know this picture is a little probably confusing when in comparison to this, I'm just looking at the nucleus part here of a uranium atom. So I'm involving changing the nucleus in some way by like splitting it apart or have radioactive decay pop off of that. So yes, chemical reactions, they can have energy changes. We've talked about endothermic and exothermic stuff before. But when it comes to nuclear reactions, because I'm messing with that really strong nuclear force, the changes in energy that is accompanied by are really, really, really large, okay? So this is what a nuclear equation looks like. So here's an example. You're like, oh my gosh, all these numbers. It's okay, we can hang with it. We know that this top number on each one of these substances in this reaction is a mass number, okay? We know that the bottom number in each one of these substances is its atomic number. All I'm showing here is what has occurred or changed between the two nuclides of beryllium-9 and helium-4 to turn them into carbon and a neutron. And some of you guys are like, what is even going on here with this neutron? I've never seen this before in my life. I can actually represent my subatomic particles in that nuclide notation with a number on top and a number on bottom meaning something, okay? So for a proton, well, mass number really just means mass, which is the number of protons and neutrons. So if I have one proton, y'all, there it is right there, a proton, yes? This bottom number we know is the atomic number, which is the number of protons. I have a proton, so I have one proton. Comparing this to neutrons, neutrons also have a mass, so it's going to have the same equivalent mass as a proton, right? But down here, I ain't got no protons. I am a neutron, okay? So you do not technically have any bottom number down there. Now, electrons are interesting. Electrons, they do not have no mass, so that top number is 0. But down here, you're like, well, how can you have a -1 proton? Technically, what we're looking at when we're looking at that atomic number is, yes, it's the number of protons. But keep in mind, a proton is a magnitude of a +1 charge. So that bottom number represents the magnitude of your positive charge. Well, an electron has the opposite of a magnitude of a positive charge. It has a -1 charge. So that's where I get that from there. Okay, so I can represent my subatomic particles as nuclear symbols too as well. Now, the cool thing that makes this stuff kind of easy is that these nuclear reactions follow the law of conservation of mass. So the total number of the atomic numbers and the total of the mass numbers on both sides of your equation must be equal on both sides. So if I look at this a little bit closer, okay, we know this arrow, this yield sign, can be kind of equivalent to an equal sign, meaning stuff on this side got equal stuff on this side. 9 + 4, that is 13. Over here, 12 + 1, that is 13. Those two numbers are equal. That means I have not defied the law of conservation of mass. Same thing down here, you guys, okay? 4 + 2 is 6, and 6 + 0 is 6. I have retained mass. I've satisfied the law of conservation of mass. So what this means is, y'all, we're just like counting and trying to add and subtract stuff, which I think is, hopefully not too challenging for us. I am going to zip my periodic table in here because this may be of aid to us when it comes to completing and balancing nuclear equations. Okay, my rooster is going crazy out there. Oh my goodness, you guys. So here I have polonium-218, and he turns into something that I do not know yet, and then lead-214. You're like, how am I supposed to do this? This arrow is an equal sign. I need to make sure the top numbers on both sides are the same. Well, 214 plus what gives you 218? And then 82 plus what gives you 84? So the first thing I'm actually going to do is I'm going to fill in these numbers right here. 4 plus 214 gives me 218. And then 2 plus 82 gives me 84. And you're like, now how do I find this symbol? Well, this bottom number is your magic number. That's my atomic number. Who is atomic number 2? It's helium. So with that, I can immediately fill in helium, okay? Moving on to the next, same mentality. All we are going to do here is we are just going to find whatever the missing numbers are on top and on bottom to complete the law of conservation of mass, and then mapping it out to what element that represents on our table. Okay, so here I had 253 plus 4. That's a total mass of 257. Right? So in order to get a total mass of 257 on here, I needed to have a 1 coming from this particle, right? 99 plus 2, that's a 101. I already have 101 on here, which means I ain't got nothing. I have a 0. You're like, who is this? Y'all, you guys, that's my neutron. Somebody who does have mass, who has a mass number of 1, but does not have any positive charge contributing to this. Amazing. Okay, next one. Doing my numbers here. I have 142 on both sides on those mass numbers. So that mass number of the missing piece here is 0. And then I have 60 on the atomic number side down here on the products. So that means in order to take this 61 down to a 60, I have to have a -1. You were like, okay, who's got that -1? Guys, that's my electron piece in there. Remember, the electron does not have any contributing positive charge. He's got a contributing negative charge. Okay, and then last one right here, we've got nitrogen 14, and it looks like he's coming together with a proton, which means the top number is a 15 and the bottom number is an 8. Let's see who is atomic number 8. Oh, y'all, that is oxygen. So this is not a big deal for us. It's actually, I think, kind of satisfying because, you know, they're fun. Now, I want us to look at this term called transmutation. Transmutation sounds like super scary, but transmutation is simply just when an element is converted into maybe a different element as a result of radioactive decay. So all of these are kind of radioactive decay type equations. We'll talk about all of the things here later, but a decay particle is a small particle that in some way changes an original atom. Okay, so if I'm looking at this this first reaction equation had a big old fat chunky polonium, and then he turned into a little helium and another big old fat thing. So this helium particle, which we'll learn what type of decay that is here in a second, is the smaller piece that shot off of this polonium atom. So I've changed polonium 218 in some way to now being lead 214. This one I've changed this guy to being now this guy. And this guy by being this guy, okay? So all of these other little teeny tiny subatomic particles are pieces of decay. So that's the transmutation that I have happening here. I'm just turning into a different element. Okay, now let's zone in on these types of radioactive decay. We're gonna go through each one of these and talk about how that affects the atom and the dangers of all and all that good stuff. And then we'll do some practice examples. Okay, alpha decay, you guys, okay? An alpha particle is emitted from the nucleus in alpha decay. Now, an alpha particle is 2 protons and 2 neutrons bound together, okay? You guys, that is the symbol for an alpha particle with its 2 and 2 to get my mass and 2 of those things being protons. This is a helium nucleus, okay? This is an alpha particle. You can see it written like this, but more often than not, you will actually see the symbol for helium. That's an alpha particle. And it can be emitted from the nucleus during radioactive decay in order for an unstable atom to become more stable. If I wanted to look at an example of an alpha decay equation, it would look something like this. This guy turns into this guy because he spits out a alpha particle or one of the other products besides the transmutation of the lead 206 that he turns into is a helium nucleus that is ejected from the atom. Now, is this alpha particle flying across the world very dangerous? Some of these radioactive decay can be dangerous. Alpha particles technically have the lowest penetrating power. If you are wearing some clothes on your body, your clothes will shield you from any of the radioactive dangers of alpha decay, which is a good thing, right? Our second type of decay is called beta decay. Now, beta particle is an electron. You were like, I thought electron had nothing to do with the nucleus. Well, it doesn't. But here's the weird thing. That electron does come from the nucleus. And the way it is able to come from the nucleus is because the process that's involved is I actually have a neutron turn into a proton. And the result of that to neutralize the overall charge of this process is you get a negatively charged electron shooting out of the nucleus. So yes, this is still nuclear decay, even though you're like, oh, it's an electron. Yes, I agree. It's kind of silly and weird, but very cool. So here's an example of a beta decay equation. Here I have carbon 14 turning into nitrogen 14. Oh, and he has done that because he has ejected an electron. This is your beta particle here, okay? Now, how powerful are beta particles? Well, they're more intense than alpha particles. They're medium-sized strength in their penetrating power. So like aluminum foil will be just fine for shielding you from your beta particles, okay? Okay, my next type of decay I think is a really interesting one too. It's called a positron. And positron is a positively charged electron, meaning it does not have mass, but it does contribute a positive 1 magnitude charge. So here's the symbol for a positron. It looks kind of exactly like an electron, except the only difference, instead of this being negative down here for your electron, it's now positive, okay? So it's a positron. Now you're like, oh, well, how does that even happen? And why is this nuclear chemistry? Well, it's emitted because I will have a proton turn into a neutron in order for that nucleus to become more stable. And the result of that is just you emit a positively charged electron or a positron. So what that looks like as an example of positron emission, I have potassium-38 turning into argon-38, and he kicks off a positron in that process to get more stable. Positrons, what are they? They seem scary, yes. Well, actually, they're unstable once they shoot off, so they'll quickly decompose. So they have like no penetrating power. There is no reason to be afraid of that, which is a good thing. Now, gamma emission, gamma rays are not a particle at all, meaning not a proton, not a neutron. I can't even really write a nuclear symbol for it. I got zeros across the board. That's just because they are high energy electromagnetic waves that are emitted from a nucleus as it changes from an excited state to a ground state. And gamma emission usually will be accompanied by one of the other types of decays. Like whenever something emits an alpha particle, usually some gamma is being shot off there too. Same thing with beta and positron emission, okay? So since I'm just pure electromagnetic radiation, you guys, these gamma rays have the highest penetrating power, okay? So only lead or concrete are gonna protect you from these super highly radioactive, dangerous gamma rays, okay? Now, my last type of radioactive decay is not really a decay, meaning a particle is not being shot off, but a particle is actually brought in to change and make the nucleus stable in some way, okay? This is called the process of electron capture. So the atom will actually pull in an electron from in its electron cloud into the nucleus, where then that electron will combine with a proton to form a neutral neutron, okay? But this will involve me dealing with the same electron particle symbol that I've been seeing here. The only difference is that I've got electron capture kind of as a reactant here, okay? He is pulling the electron in to turn into something else. So argon-38 turns into chlorine-38 by the process of capturing that electron. Amazing. Now, like I mentioned, my main three that have any penetrating strength are my alpha particle, my beta particle, and my gamma rays, right? Alpha particles are the least serious. Paper, clothes will cover you good. Beta, I'm dealing with some metal foil. And then gamma, I have to have like a thick thing of concrete and lead. So I kind of want to focus on these. These are the big three types of radioactive decay and summarize what we have learned so far.
When an unstable nucleus decays, it fires out alpha, beta, or gamma radiation. What are the three types of nuclear radiation, and what are the dangers and uses? Firstly, an alpha particle, made of 2 neutrons and 2 protons, basically a helium nucleus with a mass of 4 and a charge of +2. When a nucleus is too big, it emits an alpha particle to become smaller. An alpha particle is ejected at about 5% light speed, and has enough energy to kick electrons from atoms, turning them into ions. Alpha is the most ionising, creating 30 to 50,000 ions per centimetre of air. But being highly ionising means it quickly loses energy and stops, giving it the shortest range of about 1 to 5 centimetres in air, and it can't pass through skin. Next is a beta particle, basically a fast electron with a very small mass and a charge of -1. When a nucleus has too many neutrons, it turns one into a proton by emitting a beta particle. The beta particle is emitted at about 60% light speed. The beta particle is less ionising than alpha, creating 50 to 100 ions per centimetre of air. But because it loses energy slower, its range is larger than alpha, about 1 metre in air, up to 2 centimetres in living tissue, or 3 millimetres in aluminium. Finally, a gamma particle, the highest energy electromagnetic wave or photon, which is massless and chargeless. When a nucleus has too much energy, it releases a gamma ray to get rid of it. Gamma is the least ionising, as little as 3 to 5 ions per centimetre of air. This gives it the longest range, hundreds of kilometres in air, tens of centimetres through living tissue, and is halved in intensity by 1.2 centimetres of lead. Here's a summary of the 3 types of nuclear radiation.
Okay, so that's a good summary of kind of, I call it the big main three. But we did learn about five technically, and we can apply our knowledge now of knowing how to balance and complete nuclear equations, and we can extend that a little bit farther now to maybe see, well, what type of radioactive decay is this nuclear equation maybe leading us to. So my periodic table may be helpful for this, right? Because we've talked about this before, because I need the conservation of mass to help me out. So that means the top number, the mass numbers need to be the same. So 9 plus 4 is 13. And then on the bottom numbers here, 4 plus 2 is going to be 6. So that's my mass number here and my atomic number totals, even though it's just one over on this side. Well, how do I figure out what to write here? Well, this is an element because it's got an atomic number here of 6. And what guy is that with an atomic number of 6, you guys? That's carbon. Okay, so we've completed the decay equation. Now, since we know about my 5 types, I can be like, well, what type of decay is this? Carbon-13 is clearly breaking up into something. Okay, but I noticed something that's really interesting here. That's that helium nucleus. So that's an example of alpha decay, right, you guys? So alpha. So technically what's happening here is carbon-13 is turning into beryllium-9 through the process of transmutation, or creating a transmutation through the process of alpha decay. So that's how I indicate that this reaction is alpha, because I see a helium nucleus on the product side. Okay, that was a lot of talking, but I'm looking for that helium nucleus on the product side for an alpha decay. All right, next one. I've got thorium-234 and palladium-234. I immediately recognize that top number is the same on both sides, and I'm noticing there's only a slight difference in that bottom number, okay? So if there was no difference on the top, that is a 0, and the difference on the bottom, I have 91 over here and 90 over there, so from this 91, I need to subtract a 1. That -1 charge is blasting at me, and I know that must be an electron. Well, if it is an electron that is being produced, I have beta decay, which means that thorium-234 is now turning into palladium-234 through the process of beta decay to become more stable, right? All right, next one. Calcium-40 turns into potassium-40. All right, so let's see my numbers on top and my numbers on bottom. That top number is 0. I need nothing to make those sides more equal than they already are. But for my bottom, to add up to 20 over here, 19 plus 1 is going to be required. Here's the trick. No mass, but a charge of a 1, an atomic number of a 1, meaning that is a magnitude if it has to be a positive charge, right? So this is a positron emission, okay? That's a positively charged electron, which I'm going to get only when I have a positive 1 down on the bottom, but no mass at all, okay? So this is an example of positron emission, meaning calcium-40 decays into potassium-40 through that process to become more stable. All right, I have iodine 125 plus something turns into tellurium 125. You're like, okay, well, those top numbers are totally the same. Bottom numbers are different, okay? And the way I get the same bottom numbers on both sides, I've got to subtract 1 from that 53 to get that 52. This looks like an electron to me. Now, the only difference between this and my beta decay is beta decay ejects an electron, which means it's a product. This is on the reactant side. So what that means is we have an instance of electron capture, which is changing iodine 125 into tellurium 125. The last one that we're going to do before we're going to do a little bit of a more challenging extension is this one. And this one is actually real cute, real fun. You're like, I see no differences. I agree with you. I see no differences. One is, I got no particles involved here. Guys, this is gamma. And this is absolutely ridiculous for me to even put here as an example. You will very rarely see a gamma decay equation or even that symbol written in there because it is negligible. But we do know that the effects of gamma radiation are a little bit dangerous. So it's just helpful to know that this is actually not a transmutation at all. I have not changed the element. The other 4 ones were examples of transmutations, okay? Now this one is where we get really interesting and really fun, okay? This one says write. Oh no, I'm having to write my own equations. It's okay. Write an equation to represent the alpha decay of thorium-230. You're like, oh, this is good news for me. Alpha decay of thorium. Well, who am I starting with? Who is the guy? Who's the guy that I'm starting with? Well, thorium-230. Well, I can represent that like this, right? Where thorium's atomic symbol is written here, and we know that 230 is actually the mass number. Now I'm missing a number down here, right? So if I'm missing the number, I gotta look on the periodic table, and it looks like if I find thorium, he's right there. I've been able to identify and grab my atomic number of 90. Okay, so now I'm doing this. Well, he's undergoing alpha decay, which means he's going to break apart into an alpha particle and whatever is the result that he turns into. So alpha decay, I know one of my products. I've got to produce an alpha particle, okay? So the only thing I'm like, oh, okay, I've got to complete is basically I've created my own like skeleton here of a nuclear equation just that I need to balance now, okay? So that means I need to figure out what the top number and bottom number is, right? So 226 plus that 4 from the alpha particle will get that 230. And then 88 plus that 2 from my alpha particle will give me the 90 that I'm needing. To figure out what element it is, I just have to find 88. And 88, you cannot even see, is radium, right? So what has happened here is through the process of ejecting an alpha particle, thorium-230 has turned into radium-226. So this is a transmutation, okay? Keep in mind, transmutations are when I turn one element into another, and that has to involve a change in that bottom number of the atomic number in some way. Very cool, very fun. So this is our brief little lesson on radioactive decay. My rooster has played a prominent part. I hope you guys can kind of hear that in the background, and I'm sorry for that. But this was a cute little fun lesson. Hopefully with the adding and subtracting, we should not have very many problems with being able to balance and write our own decay equations.